Imagine yourself drifting gently through space. There is no sound here. No wind, no rushing air, no distant hum of machines. The universe at this scale is almost perfectly silent. Yet around you, something immense is quietly unfolding. You float inside a nebula. A nebula is not a single object, but a vast cloud and ocean of gas and dust that stretches across light years of space. If you could see it from far away, it might appear as a glowing veil painted across the darkness. Colors swirl through it, soft blues, faint violets, deep crimson reds. These colors come from energized gases slowly shining in the cold vacuum. But from where you drift now, inside the cloud itself, it feels different. The nebula is thin. Much thinner than any cloud in Earth's sky. In fact, if you could scoop a handful of this cosmic mist, it would feel almost like nothing at all. A few atoms here. A tiny grain of dust there. Enormous distances separate each particle. And yet, over distances so large that the human mind struggles to picture them, these scattered particles form one of the most important structures in the universe. Because this is where stars are born. You drift slowly through the cloud, and everywhere around you float atoms of hydrogen. Hydrogen is the simplest element in existence. Each atom is just a single proton, sometimes accompanied by an electron. Nothing complicated. Nothing elaborate. But simplicity can hide remarkable potential. Nearly all the hydrogen in this nebula has been traveling through space for billions of years. Some of it formed shortly after the universe itself began. Long before galaxies fully formed. Long before planets existed. Long before any living creature opened its eyes beneath a sky. These atoms have wandered the cosmos for ages. And now, quietly, they gather here. A nebula may stretch across dozens or even hundreds of light years. To give your mind something familiar to hold on to, remember that 1 light year is the distance light travels in a full year, about 9 trillion kilometers. So this cloud is not merely large. It is almost unimaginably vast. And still, within this enormous drifting ocean, the smallest movements begin to matter. Very slowly, particles begin to drift closer together. Not because they want to. Not because they are being pushed. But because of gravity. Gravity is the quiet architect of the universe. It is the same gentle force that holds your feet to the earth, that guides the moon around our planet, and that keeps the planets circling the sun. But here in the nebula, gravity works at a pace that feels almost like stillness. 2 hydrogen atoms drift slightly closer together. Another floats past and joins them. Then another. The movement is so subtle you might not notice it at first. If you watched for a few seconds, or even a few years, the cloud would seem unchanged. But time in the universe is patient. Given thousands, millions, even tens of millions of years, these tiny shifts begin to accumulate. Slowly, certain regions of the nebula become just a little denser than the rest. Not dramatically denser. Just enough that gravity begins to strengthen its grip. You might imagine it like a calm lake on a windless night. At first the water is smooth everywhere. But eventually, gentle currents begin to form beneath the surface. Small motions gather together, guiding water towards certain places. The nebula behaves in a similar way. Invisible rivers of gas drift through the cloud, guiding hydrogen atoms into slightly thicker regions. Dust grains, tiny specks of carbon, silicon, and ice, float along these currents like cosmic pollen. These dust grains are older than you might imagine. Some of them were once part of ancient stars that exploded long ago. Those stars scattered their atoms across the galaxy, and over millions of years those atoms cooled, condensed, and joined this new cloud. So even here, in what seems like the beginning of a star's life, there are echoes of older stars that came before. The universe is full of such quiet cycles. You continue drifting deeper into the nebula. The cloud around you grows slightly thicker. The particles are still far apart, but they are no longer perfectly scattered. Something subtle is changing. Gravity is slowly pulling matter inward. Imagine invisible threads stretching between every particle of gas. Each atom gently tugs on every other atom. The pull is incredibly weak, but across such enormous distances, and over such immense time, the effect becomes meaningful. Little by little, the cloud begins to gather itself. This is not a collapse in the dramatic sense. There are no sudden crashes. No rushing storms. Instead, the nebula slowly folds inward, like a blanket settling softly onto a bed. Where the cloud thickens, gravity grows stronger. Where gravity grows stronger, more gas begins to drift inward. And so the process feeds itself. Astronomers sometimes call these regions stellar nurseries, because they are the places where new stars quietly begin to take shape. But right now, nothing yet resembles a star. There is no bright light. No blazing fire. Only a slow gathering. You might notice that some regions of the nebula appear darker than others. These darker patches are known as molecular clouds, areas where gas and dust are thick enough to block distant starlight. Inside these shadowy pockets, something important is happening. The gas is cooling. Cooling may sound unimportant, but in space it matters greatly. When gas becomes colder, its particles move more slowly. When particles move more slowly, gravity has an easier time drawing them together. So these dark clouds become the perfect places for future stars to begin forming. You drift into one of these quiet regions. The darkness deepens slightly, not because light has disappeared, but because the surrounding dust gently absorbs and scatters it. Here, the cosmic cloud is slowly tightening its embrace. Hydrogen gathers. Dust drifts inward. Gravity patiently continues its work. And somewhere deep within this vast drifting cloud, an invisible boundary is beginning to form, a region where matter has gathered just enough that the collapse can no longer stop itself. At first it will be almost impossible to see. A slight thickening of gas. A gentle inward motion. But over time, this gathering will become stronger, denser, warmer. Eventually, the quiet cloud will form a glowing center. A young object. Not yet a star, but the earliest stage of one. For now, however, you simply float in the silent nebula, surrounded by ancient atoms slowly drifting together. Nothing feels urgent. Nothing feels sudden. The universe is taking its time. Yet within this calm and spacious cloud, gravity is patiently weaving the first threads of a future sun. And if you linger here long enough, watching the gas slowly gather in the darkness, you may begin to notice something subtle. The cloud is no longer perfectly still. Somewhere within it, the gentle pull of gravity is beginning to grow stronger. You remain suspended inside the vast nebula. Around you, the cloud still appears calm, almost motionless. The particles drifting through this cosmic fog move so slowly that even centuries would reveal little obvious change. But the universe rarely reveals its deepest processes through sudden motion. Instead, it works quietly, patiently, over spans of time so large that change becomes nearly invisible. Yet change is happening. You begin to notice that the region around you feels slightly different now. The scattered hydrogen atoms are no longer evenly spread across the cloud. Some areas are beginning to thicken, like mist gathering more densely in certain valleys on an early morning. This gentle gathering is the work of gravity. Gravity is often imagined as something dramatic: planets falling towards stars, objects dropping to the ground, black holes pulling light into darkness. But gravity's most important work in the universe is often its quietest work. It is a force that never sleeps. Every particle with mass attracts every other particle with mass. The pull between two hydrogen atoms is incredibly small, so small that it might seem meaningless. But inside a nebula containing trillions upon trillions of atoms, these tiny pulls begin to add together. Each atom gently calls to the others. And slowly, the cloud begins to listen. You drift through one region of the nebula where the gas is just a little thicker than its surroundings. The difference is subtle, but it matters. In this region, gravity's influence becomes slightly stronger. Not dramatically stronger, just enough to encourage nearby particles to drift inward. Imagine standing in a shallow valley after rain. Water from the surrounding hills quietly flows down toward the lowest point. No single drop seems powerful on its own, yet together they gather into a small pool. In the nebula, hydrogen atoms behave in a similar way. They slowly move toward the denser regions of the cloud, guided by gravity's gentle hand. At first, the inward motion is almost impossible to detect. Atoms drift only slightly closer together, their movement measured in kilometers across thousands of years. But gravity does not rush. It simply continues. As more atoms gather, the region becomes denser. And as the region becomes denser, its gravitational pull grows stronger. This is how the process begins to build momentum. The cloud is not collapsing violently. Instead, it is quietly tightening, like a loose knot slowly being drawn inward. You notice another subtle change as this happens. The gas begins to warm. This may sound surprising at first. After all, space is extremely cold. Temperatures inside a nebula can fall to just a few degrees above absolute zero. Yet as gravity pulls gas inward, something important begins to happen. The particles start moving faster. When atoms fall inward under gravity, they convert gravitational energy into motion. As they drift closer together, they bump into one another more frequently. These tiny collisions cause the gas to warm ever so slightly. The warmth is faint at first, barely noticeable. But it is the beginning of something important. You drift deeper into the gathering cloud, and now you can begin to imagine its shape. The once evenly scattered gas is slowly forming clumps, regions where matter collects more strongly. Astronomers call these regions dense cores. Each dense core is like a tiny seed planted inside the nebula. Within it, gravity is beginning to dominate the motion of the gas. The outward drifting that once kept the clouds spread thin is slowly losing its balance. Gravity is winning. But the universe rarely allows a process to move in only one direction. Even here, forces compete gently against one another. Gas particles still carry energy from their motion. They push outward as they move and collide, trying to keep the cloud expanded. Magnetic fields threading through the nebula also resist the collapse slightly, adding delicate tension to the cloud structure. For a long time, these opposing forces maintain a fragile balance. Gravity pulls inward. Gas pressure pushes outward. The cloud lingers between these two influences, hovering on the edge of transformation. You might imagine it as a slow, deep breath held by the universe. But over time, gravity gains the advantage. More gas drifts inward. The dense core grows heavier. The inward pull strengthens. Eventually, a quiet threshold is crossed. The moment is not dramatic. There is no flash of light or sudden movement. Yet it marks an important turning point. The core has gathered enough mass that gravity's pull can no longer be balanced by the outward pressure of the gas. The collapse becomes inevitable. You begin to sense the change. Particles that once drifted slowly now move slightly faster toward the center of the dense core. Dust grains swirl gently along invisible currents, spiraling inward like leaves drawn toward the center of a slow whirlpool. The cloud is no longer simply drifting. It is contracting. Still, the process remains peaceful. Even as the collapse begins, the timescale is enormous. Tens of thousands of years pass while the gas gradually falls inward. From your quiet vantage point inside the nebula, the motion still feels gentle and graceful. The cloud folds inward like a soft curtain being slowly drawn closed. And as it does, the temperature in the center continues to rise. Not enough to produce light yet. Not enough to ignite any kind of stellar fire. But enough to hint at what is coming. You drift closer to the heart of this collapsing region. The density here is higher now. Hydrogen atoms pass by more frequently, and the dust between them glimmers faintly in scattered starlight filtering through the surrounding cloud. At the center, something new is beginning to form. The gas is gathering into a small, warm core. It is not yet a star. But it is no longer just a cloud. Gravity continues pulling material inward from every direction, feeding the growing center with a slow and steady stream of gas. The core thickens, warms, and grows heavier with each passing millennium. If you could watch this process unfold across millions of years, you would see the clouds slowly transform. The loose mist of the nebula becomes a tightening sphere. The sphere gathers mass. The center grows hotter. And gradually, quietly, the next stage of a star's life begins to emerge. For deep within this slowly collapsing cloud, gravity is shaping something new. Something warmer. Something brighter. Something that will soon become a glowing object hidden inside the surrounding gas. Astronomers have a name for this fragile, early stage of stellar life. They call it a protostar. And as the cloud continues to contract around you, the faint heart of that protostar is just beginning to awaken. You drift quietly toward the heart of the collapsing cloud. The nebula around you still stretches for light years in every direction, but here, near the center of the dense core, something feels different. The once scattered gas is no longer drifting aimlessly. Now it moves with purpose, slowly falling inward toward a growing center. Gravity has begun to shape the cloud into something new. The inward pull that started as a gentle suggestion has now become a steady guide. Hydrogen atoms, tiny grains of dust, and faint traces of other elements all flow toward the same destination. The motion is still calm, still slow by human standards, but compared to the quiet stillness of the earlier nebula, the change is unmistakable. The cloud is forming a heart. At the very center of this gathering material, a warm, dense object is beginning to appear. It is small compared to the enormous nebula surrounding it, yet it holds an increasingly powerful influence over the gas around it. Astronomers call this early object a protostar. A protostar is not yet a true star. It has not ignited the brilliant nuclear fire that will one day define it. But it is already something remarkable, a young star in the earliest stage of its life. You move closer to the forming protostar. Around it, the gas no longer falls inward evenly from every direction. Instead, something interesting begins to happen. The collapsing cloud starts to spin. Even the quietest regions of space carry tiny amounts of rotation. When the nebula first began collapsing, it already possessed a faint spin, so subtle it was almost impossible to notice. But as gravity pulls the cloud inward, that slow rotation becomes stronger. This happens for the same reason a spinning ice skater turns faster when pulling their arms inward. As the cloud contracts, its rotation speeds up. Gradually, the inward falling gas flattens into a wide, rotating disk around the protostar. This structure is known as a protoplanetary disk, a vast, slowly spinning disk of gas and dust that surrounds the growing star like a cosmic whirlpool. You float near the edge of this disk. Dust particles swirl gently along curved paths, tracing invisible lines through space. Each tiny grain is no larger than smoke or fine sand, yet together they form a shimmering ring stretching billions of kilometers across. In the distant future, parts of this disk may slowly gather into planets, moons, asteroids, and comets. But for now, its purpose is simpler. It feeds the young star. Gas continues to spiral inward through the disk, slowly falling toward the protostar at the center. As this material descends deeper into the growing object's gravity, something fascinating happens. It releases energy. Every particle falling inward converts gravitational energy into heat. As the gas compresses and collides with itself, the temperature inside the protostar steadily climbs. At first the warmth is faint. Then it grows stronger. The center of the protostar becomes hotter and denser with each passing century. If you could measure the temperature deep within its core, you would find it already reaching thousands of degrees. Far hotter than the surfaces of most planets. Hot enough to make atoms move with increasing speed and energy. Yet even now, the protostar remains hidden from the wider universe. The thick gas and dust of the surrounding nebula absorb most of the light escaping from its warm surface. From far away, the young star would appear dim and shrouded, wrapped in the cloud that gave birth to it. But here, close to its center, you can sense the growing energy. The protostar is slowly brightening. Not because nuclear fusion has begun yet, but because gravity itself is heating the gas. The collapse continues, feeding the protostar with new material, and each incoming particle adds a tiny amount of warmth to the growing core. The process is steady, patient, unhurried. You drift along the edge of the spinning disk and notice another beautiful detail of this early stellar stage. Two narrow streams of glowing gas shoot outward from the poles of the protostar. These are known as stellar jets. They emerge from the young star like twin fountains of light, extending vast distances into the surrounding nebula. The jets form as powerful magnetic fields channel some of the infalling gas away from the star, launching it outward at incredible speeds. Even though the protostar is still young and hidden, these jets announce its presence to the cosmos. They carve long tunnels through the surrounding cloud, clearing pathways through the dust and gas that once surrounded the forming star. Gradually, the protostar becomes easier to see. More light escapes. More warmth fills the region. But the true transformation has not happened yet. Deep inside the protostar, gravity continues compressing the core. The pressure grows immense. Hydrogen atoms are squeezed closer and closer together, forced into tighter and tighter spaces. As the compression continues, the temperature rises further. 10,000 degrees. 50,000 degrees. Hundreds of thousands of degrees. The numbers climb slowly but steadily. Each increase in temperature pushes the protostar closer to a remarkable threshold, one that will transform it forever. But that moment still lies ahead. For now, the protostar remains in a delicate stage of growth. It gathers mass from the surrounding disk, slowly becoming heavier and hotter. The inward flow of gas continues, feeding it like a quiet river of matter. Some protostars grow slowly. Others gather material more quickly. The final mass of the star will determine much of its future life, how bright it will shine, how long it will live, and how it will eventually die. But in this early stage, the protostar is simply learning how to exist. It breathes in gas from its surroundings. It radiates gentle warmth into the nebula. And with each passing century, its core becomes a little hotter, a little denser, a little closer to the moment when the true fire of a star will ignite. You drift quietly near the glowing center of the disk and watch the slow currents of gas spiral inward. Everything here feels calm, yet full of anticipation. The protostar is like a candle that has been carefully prepared but not yet lit. All the ingredients for a star are now present: mass, gravity, pressure, and heat. Only one final step remains. Deep inside the core, hydrogen atoms are beginning to move with extraordinary energy. Soon, they will collide with such force that something extraordinary will happen. Two atoms will merge. A new form of energy will burst into existence. And the quiet warmth of the protostar will transform into a brilliant and steady stellar fire. But that moment has not arrived just yet. For now, gravity continues its patient work, drawing the young star closer and closer to the threshold where fire is finally born. You drift close to the young protostar, watching the slow currents of gas spiral inward through the surrounding disk. For a long time, gravity has been gathering matter here, quietly shaping the cloud into a growing sphere of warmth and pressure. The protostar now holds a great deal of mass, far more than when the nebula first began to collapse. Its gravity has become strong, and the gas falling inward continues feeding the dense center. Yet the most important changes are happening where you cannot easily see them. Deep inside the protostar's core. If you could journey inward past the swirling disk, through the glowing outer layers, and into the very center, you would discover a place unlike any other in the young star. Here, the pressure is immense. the weight of all the gas above presses inward toward the core. Each layer of hydrogen pushes down upon the layers beneath it, squeezing the central region tighter and tighter. The atoms that once drifted freely inside the nebula are now packed far closer together. And with this pressure comes heat. Temperature rises steadily as gravity continues its slow work. At first the core warmed to a few thousand degrees, then tens of thousands. Over time, the heat climbed even higher. Hundreds of thousands of degrees. Then millions. Inside this hidden furnace, hydrogen atoms move faster and faster. They collide with tremendous energy, bouncing apart again and again. The gas becomes so hot that the atoms no longer behave in the quiet, stable way they once did. Electrons break free from their atoms, leaving behind bare nuclei, tiny positively charged particles racing through a sea of energy. This state of matter is called plasma. In plasma, the gas behaves differently from the familiar air around you on Earth. Charged particles swirl through magnetic fields, collide with incredible force, and respond quickly to changes in pressure and temperature. The protostar is now filled with this energetic plasma. Still, even with all this heat and motion, something remarkable has not yet happened. The star has not ignited. Because for nuclear fusion to begin, the process that powers every true star, the core must reach an extraordinary temperature. About 10 million degrees. It takes patience for the universe to reach such extremes. For hundreds of thousands of years, gravity continues compressing the core. Each moment adds a little more pressure, a little more heat, a little more motion to the crowded hydrogen nuclei racing through the center. And gradually, quietly, the threshold approaches. You might imagine hydrogen nuclei as tiny spheres of positive charge. Because they share the same electric charge, they naturally repel each other, pushing away when they come too close. This repulsion normally keeps them apart. Even in the hot plasma of the protostar, most collisions simply send the particles bouncing away again. But as the temperature climbs higher, the nuclei move faster and faster. Their collisions grow more violent. Occasionally, two hydrogen nuclei approach each other with such tremendous speed that they manage to overcome their electrical repulsion. For a fleeting instant, they come close enough for another force of nature to take over. The strong nuclear force. This force acts only across extremely tiny distances, but it is incredibly powerful. When two nuclei come close enough, the strong force pulls them together, binding them into a new atomic structure. This moment is the beginning of nuclear fusion. Inside the core of the protostar, two hydrogen nuclei merge to form a slightly heavier nucleus. In the process, a tiny fraction of their mass is converted directly into energy. Not chemical energy like a burning fire. Something far greater. Pure energy, released according to one of the most famous principles in physics, the relationship between mass and energy. Even the smallest amount of mass can produce an enormous burst of energy when converted in this way. At first, only a few fusion reactions occur. The conditions inside the core are just barely hot enough. But with each reaction, a small amount of energy spreads outward into the surrounding plasma. That energy adds heat. And that heat increases the chances of more fusion events occurring. Soon, the process begins to grow. More hydrogen nuclei collide. More fusion reactions occur. More energy pours into the core. The protostar has reached a turning point. For millions of years, gravity has been the dominant force shaping the young star. It pulled the cloud inward, compressed the gas, and heated the core. But now a new force enters the balance. The energy from nuclear fusion begins pushing outward. Inside the star, an extraordinary balance begins to form. Gravity continues pulling matter inward toward the center. Fusion energy pushes outward, resisting that collapse. When these two forces reach equilibrium, perfectly balancing one another, the star stabilizes. This moment marks the true birth of a star. The protostar becomes something new. A main sequence star. Its inner fire is now self-sustaining. Nuclear fusion in the core produces a steady stream of energy that flows outward through the star's layers. That energy eventually escapes into space as light and heat. The star begins to shine. At first, the surrounding gas and dust still hide much of the light. But the intense radiation slowly clears the cloud away. Stellar winds, streams of charged particles flowing outward from the star, push the remaining nebula aside. Gradually, the newborn star emerges. From a distance, it appears as a brilliant point of light shining against the darkness of space. What began as a faint gathering of hydrogen atoms inside a drifting nebula has now become a blazing sphere of plasma millions of kilometers wide. And at its center, fusion continues. Hydrogen nuclei merge into helium. Energy flows outward. Light travels across space. You watch this transformation with quiet wonder. The star has awakened. Yet despite its fiery core, the star's life from this point forward will be surprisingly calm. For most of its existence, it will shine steadily, maintaining the delicate balance between gravity and fusion. This stable phase may last millions, or billions, of years. But that long and peaceful chapter of stellar life is only just beginning. For now, the newborn star settles into its steady rhythm, its inner fire burning quietly in the depths of space. And as the light spreads outward through the cosmos, a long and tranquil era of stellar life begins to unfold. The star has finally awakened. After millions of years of gathering, collapsing, and warming, the brilliant fire of nuclear fusion now burns steadily at its center. The transformation that began inside a drifting nebula has reached a remarkable new stage. You drift quietly nearby, watching the young star glow against the dark ocean of space. Its light spreads outward in all directions, flowing like a gentle tide of energy into the surrounding cosmos. Photons, tiny packets of light, stream away from its surface, beginning journeys that may last thousands, millions, or even billions of years before they encounter another object in the universe. Some of that light may one day touch distant planets. Some may pass through clouds of gas and dust. Some may travel endlessly through empty space. But all of it begins here, deep within the star's core. Inside that hidden center, hydrogen atoms are continuing their quiet transformation. The temperature there reaches millions of degrees, and the pressure is almost impossible to imagine. Hydrogen nuclei move through the dense plasma with extraordinary speed, colliding again and again. Every so often, two of those nuclei come close enough for the strong nuclear force to bind them together. When that happens, nuclear fusion occurs. Two hydrogen nuclei merge, forming helium and releasing energy in the process. This energy begins its slow journey outward through the layers of the star. But the journey is not simple. The star is incredibly dense. Photons created in the core cannot escape directly to space. Instead, they are absorbed, re-emitted, scattered, and redirected countless times by the surrounding plasma. A single photon may take thousands of years, sometimes even hundreds of thousands of years, to travel from the core to the surface. You might imagine it like a traveler trying to leave a crowded city, constantly stopped by busy intersections and winding streets. Progress is slow, indirect, and full of detours. Yet eventually, the light reaches the outer layers. From there, it escapes freely into the darkness of space. And so the star shines. What makes this stage of the star's life remarkable is not its intensity, but its balance. Inside the star, two powerful forces are now locked in a quiet and stable partnership. Gravity continues pulling inward, trying to compress the star further. The enormous mass of the star presses down toward the center, constantly attempting to collapse the entire sphere. But the energy from nuclear fusion pushes outward. The heat generated in the core creates pressure in the star's interior plasma. That pressure resists gravity's pull, holding the star open and stable. When these two forces perfectly balance each other, the star enters what astronomers call the main sequence. This is the longest and most stable phase of a star's life. During this time, the star behaves almost like a perfectly tuned instrument. Every moment, fusion in the core releases just enough energy to counteract gravity's inward pull. Not too much. Not too little. The result is a steady, glowing sphere that can shine for extraordinary lengths of time. If the star is very massive, it burns its fuel quickly, living only a few million years. But if the star is smaller and more modest, like the sun in your own solar system, it can continue shining for billions of years. The pace of fusion depends on the star's mass. Larger stars have stronger gravity pressing on their cores. This creates higher temperatures and faster fusion reactions. As a result, they burn through their hydrogen fuel much more quickly. Smaller stars, on the other hand, fuse hydrogen more gently. Their cores are cooler, their fusion slower, and their lifetimes far longer. Some small stars may shine quietly for hundreds of billions of years, far longer than the universe has existed so far. But regardless of their size, all stars share this long, peaceful stage. It is the calm middle chapter of their lives. You watch as the star continues its quiet work. Hydrogen becomes helium. Energy flows outward. Light travels into the vastness of space. From the outside, the star appears perfectly steady. Its brightness remains almost constant. Its shape stays nearly unchanged. It shines with the quiet confidence of something that has found its balance. Yet deep within the core, change is slowly unfolding.
Every fusion reaction transforms a tiny amount of hydrogen into helium. At first, this change is almost impossible to notice. The core still contains enormous reserves of hydrogen fuel. But over millions and billions of years, the balance gradually shifts. Helium begins to accumulate in the center of the star. Unlike hydrogen, helium does not fuse easily at the temperatures currently present in the core. So it gathers quietly, forming a slowly growing region of heavier gas at the very center. Meanwhile, the hydrogen surrounding that helium core continues to fuse. The star keeps shining. Its light warms distant space. Its gravity may guide planets into stable orbits. Its radiation may influence nearby clouds of gas and dust. In this stage of life, a star can become the heart of an entire solar system. Planets may form within the leftover disk of material surrounding it. Asteroids and comets may drift through its gravitational field. If conditions are right, worlds may emerge where oceans form, atmospheres gather, and life slowly evolves beneath the steady warmth of the star. All of this becomes possible because of the quiet stability of the main sequence. The star provides a reliable source of light and energy for millions or billions of years. From your vantage point in space, the star appears calm, confident, almost eternal. But the universe knows that nothing remains unchanged forever. Deep in the star's heart, the slow transformation continues. Hydrogen disappears. Helium grows. The core becomes slightly denser with each passing age. For a very long time, the star adjusts gently to these changes. The fusion reactions shift subtly, maintaining the delicate balance between gravity and pressure. But eventually, the star will face a new challenge. One day, the hydrogen in the core will begin to run low. Fusion will weaken. Gravity will once again begin to tighten its grip. And the calm stability that has defined this long chapter of stellar life will slowly begin to fade. For now, though, the star continues shining peacefully, sending its light into the universe with quiet patience. Yet deep inside its glowing heart, the first subtle signs of change are already beginning to appear. For an immense span of time, the star has lived in quiet balance. Its core has steadily fused hydrogen into helium, releasing the energy that keeps gravity in check. The light pouring from its surface has traveled across space in a continuous, calm stream. From afar, nothing about the star seemed to change. But deep inside, the story has always been slowly moving forward. You drift closer to the glowing sphere and imagine its interior layers. Beneath the bright surface lies a vast ocean of hot plasma, slowly circulating and carrying energy outward from the core. And at the center of it all sits the engine that has powered the star for most of its life. But that engine is beginning to change. Inside the core, the supply of hydrogen is no longer endless. For millions or billions of years, hydrogen atoms have collided and fused, creating helium and releasing tremendous energy. Each fusion reaction removed a tiny bit of hydrogen from the core, quietly replacing it with heavier helium. At first, this change was barely noticeable. The core still contained enormous amounts of hydrogen fuel, and the star easily maintained its steady rhythm. But as time passes, the balance begins to shift. Helium slowly accumulates at the center of the star. Unlike hydrogen, helium requires far greater temperatures and pressures to fuse. Under the current conditions inside the core, helium remains mostly inactive. It gathers quietly, forming a dense central region that grows larger with time. Meanwhile, the surrounding hydrogen continues to burn. You might imagine the star's interior as a glowing shell surrounding a heavier heart. Fusion reactions now occur in a region just outside the helium core, where hydrogen still remains plentiful. But the core itself is changing. Without active fusion to generate outward pressure, gravity begins pressing inward more strongly on this helium center. The core slowly contracts, becoming denser and hotter as it shrinks. This compression releases additional heat, and as the core warms, the surrounding hydrogen shell begins to fuse even faster. The star responds to this increase in energy in a surprising way. Its outer layers begin to expand. Slowly at first, almost imperceptibly, the star begins to swell. The surface moves outward into space, stretching farther from the core that once held it tightly in place. As the star expands, its surface temperature cools slightly. The light it emits shifts toward warmer, reddish tones. From far away, the star now appears larger and softer in color, glowing with a deep orange or red hue instead of the bright white or yellow it once displayed. This transformation marks the beginning of a new stage of stellar life. The star is leaving the long, stable chapter known as the main sequence. You float nearby and watch as the star grows gradually larger. Its atmosphere becomes more extended, reaching farther into space than before. The outer layers of plasma drift outward gently, forming a vast envelope around the contracting core. Inside, the changes continue. The helium core becomes increasingly dense as gravity compresses it. Temperatures climb steadily, reaching tens of millions of degrees. The pressure grows immense, pushing the atoms within the core closer together than ever before. Yet helium still refuses to ignite. The conditions are not quite extreme enough. For now, the core continues its quiet collapse, growing hotter and denser with time. Around it, the hydrogen-burning shell produces tremendous energy. This shell fusion generates more power than the star's core once did during its stable years. That extra energy flows outward, pushing the outer layers even farther away. The star swells to enormous size. If this were happening to a star like the Sun, its outer atmosphere might eventually stretch outward far enough to swallow the inner planets of its solar system. Mercury might vanish first, then Venus, and eventually perhaps even Earth itself. Yet despite this dramatic expansion, the star's life still moves slowly. Thousands of years pass as the transformation unfolds. The star does not explode or collapse suddenly. Instead, it gently reshapes itself. You watch as the star continues its slow transformation. What was once a compact, steady sphere has begun to change shape in subtle but unmistakable ways. The outer layers, once held tightly by gravity and balanced by the steady energy of fusion, now drift outward into space. The star is expanding. At first, the change is gradual. Over thousands of years, the surface moves farther from the center, stretching outward like a slowly inflating balloon. The star grows larger, its atmosphere spreading across distances that would once have seemed impossible. Yet even as the star grows, its surface cools. When a sphere expands, its energy spreads across a larger area. The light coming from the star becomes softer, warmer in color. What was once a bright yellow or white glow now shifts toward deep orange and red. This is why astronomers call this stage of stellar life a red giant. From afar, the star now appears enormous and gentle, glowing with a reddish hue that spreads quietly into the surrounding darkness. But the true story of the red giant is not happening on its surface. It is unfolding deep inside the star's core. At the center lies the dense sphere of helium that has been slowly forming for millions or billions of years. This core has continued shrinking under the weight of the layers above it. Gravity presses inward, squeezing the helium atoms closer and closer together. The pressure is almost beyond imagination. The temperature rises steadily as the core contracts. Tens of millions of degrees fill this hidden region. The helium atoms move faster and faster, colliding within the dense plasma. Yet even under these extreme conditions, helium remains stubborn. It does not fuse easily. The star must continue compressing its core until the temperature climbs even higher, high enough to overcome the resistance of helium nuclei and allow them to merge. While the core prepares for this moment, The surrounding hydrogen shell continues its work. Hydrogen fusion now occurs in a thin layer surrounding the helium core, producing tremendous energy. This shell burns more intensely than the original core once did, sending enormous amounts of heat outward through the star. That extra energy pushes the outer layers even farther into space. And so the red giant continues to grow. Its atmosphere becomes vast and diffuse, stretching outward millions of kilometers beyond its original size. The outer layers are no longer tightly bound together. They form a soft, extended envelope of glowing gas surrounding the dense inner regions. If you could float within these outer layers, you might barely notice the star's presence. The gas is thin, drifting slowly, like a luminous fog spread across space. Yet despite its softness, the star now occupies an enormous volume. A red giant can grow hundreds of times larger than it once was. Imagine a star the size of your sun expanding so greatly that its outer atmosphere reaches the orbit of distant planets. The star's gravity still holds its gas together, but its shape becomes vast and gentle, almost fragile in appearance. From a distance, the red giant glows like a quiet lantern in the dark. You drift closer and sense the slow motion of the star's outer layers. They rise and fall gently, like tides in a glowing ocean. Vast currents of plasma move through the atmosphere, carrying heat from the interior toward the surface. Inside the star, convection begins to play an important role. Hot gas from deeper layers rises upward, cooling as it approaches the surface before slowly sinking again. These enormous convective currents create patterns across the star's atmosphere, slowly reshaping the glowing clouds of gas. Yet even as the surface appears calm and beautiful, the core continues its silent preparation. The helium heart of the star grows hotter and denser with every passing century. Gravity presses inward. Pressure increases. And the temperature continues climbing toward an extraordinary threshold. Eventually, the core will reach a temperature of nearly 100 million degrees. Only then will helium fusion finally ignite. But before that moment arrives, the star remains in this majestic stage of expansion. The red giant shines steadily, though its energy now comes from the hydrogen shell surrounding the core. The star's light grows brighter overall, even as its surface temperature cools. This combination, greater brightness but cooler surface temperature, is what gives red giants their distinctive glow. You watch as the enormous star fills the surrounding darkness with its warm reddish light. What once seemed like a quiet ending has instead become a grand transformation. The star has not faded. It has grown. It has become larger, slower, more luminous in its final middle age. And within its expanding atmosphere, new possibilities are quietly forming. Because inside this enormous star, the conditions are slowly approaching something extraordinary. The core is nearing the temperature required for a new kind of fusion, one that will begin creating entirely new elements. Elements that did not exist when the star was first born. Carbon, oxygen, and others that will one day become part of planets, oceans, mountains, and even living creatures. But that remarkable transformation has not quite begun. For now, the red giant continues its slow cosmic bloom, its enormous atmosphere glowing gently across the quiet depths of space. And deep inside its hidden core, the next great fire of stellar life is patiently preparing to ignite. You remain beside the enormous red giant as it glows quietly in the darkness. From the outside, the star appears calm, almost peaceful. Its vast outer atmosphere drifts slowly outward, glowing with a warm reddish light. Gentle currents of plasma rise and fall across its surface, like glowing waves. But deep within the star, something extraordinary is about to happen. For a long time, the core has been slowly shrinking under the steady pressure of gravity. The helium gathered at the center has grown denser and hotter with each passing century. The temperature has climbed steadily, rising from tens of millions of degrees toward a far more intense threshold. Now, the core approaches nearly 100 million degrees. At such temperatures, the behavior of matter becomes almost unimaginable. Helium nuclei, each made of 2 protons and 2 neutrons, move through the dense plasma at incredible speeds. They collide again and again, bouncing apart as their electric charges push them away from one another. But occasionally, something remarkable occurs. 3 helium nuclei come together in a delicate and rare sequence of events. When this happens, they fuse into a new atomic nucleus. Carbon. This process is known as the triple alpha reaction. The name comes from the fact that helium nuclei are sometimes called alpha particles. When 3 of them merge, they form carbon, one of the most important elements in the universe. And just like the earlier fusion of hydrogen, this reaction releases energy. For the first time since the star left the main sequence, a new type of nuclear fire ignites inside the core. Helium fusion has begun. The moment this happens, the star experiences a dramatic internal change. Inside certain stars, especially those similar in mass to your Sun, the ignition of helium happens suddenly in an event astronomers call the helium flash. Despite the dramatic name, this event remains hidden deep inside the star and cannot be seen from outside. But internally, it is powerful. For a brief period, helium fusion surges through the core, releasing enormous amounts of energy. This sudden burst relieves the crushing pressure that gravity had built up during the long contraction of the core. The core stabilizes. The helium begins fusing steadily into carbon and sometimes into oxygen as well. The star settles into a new balance. Now, the red giant contains 2 fusion zones. At the very center, helium nuclei fuse together to create heavier elements. Surrounding that core, a shell of hydrogen continues fusing into helium just as it has for millions of years. 2 layers of nuclear fire now burn within the star. The result is a remarkable cosmic furnace. You drift closer and imagine the processes unfolding within this immense sphere of plasma. Helium nuclei collide and merge, forming carbon. Sometimes, carbon nuclei capture additional helium atoms, forming oxygen. These elements are heavier and more complex than the simple hydrogen that once filled the nebula where the star began its life. And yet here they are, being created deep inside this aging star. It is a quiet act of cosmic craftsmanship. Every carbon atom that forms inside the core will one day drift into the wider universe. Every oxygen nucleus produced here may someday become part of distant planets, icy comets, or the atmospheres of future worlds. Even the oxygen you breathe and the carbon in your own body were forged long ago inside stars like this one. You are watching the universe slowly create the ingredients of life. Inside the red giant, convection currents begin carrying some of these newly formed elements outward. Hot plasma rises from deeper layers, transporting traces of carbon and oxygen toward the outer regions of the star. Over long spans of time, these materials mix throughout the star's interior. The red giant becomes not only a source of light, but also a factory of elements. And the universe depends on this process. When the universe first formed, It contained mostly hydrogen and helium. These simple elements filled the earliest galaxies and nebulae. But the complex chemistry needed for planets, oceans, rocks, and living organisms did not yet exist. Stars had to create those elements. And so generation after generation of stars quietly performed this work, fusing lighter atoms into heavier ones deep inside their cores. You float beside the glowing red giant and sense the profound patience of this process. The star does not rush. Helium fusion continues steadily for hundreds of thousands, sometimes millions of years. Carbon accumulates in the core while oxygen slowly joins it. The structure of the star grows increasingly layered, like a cosmic onion. At the center lies the dense core of carbon and oxygen. Around it burns a shell where helium continues to fuse. Outside that lies the hydrogen-burning shell. And far beyond all of this stretches the enormous atmosphere of the red giant itself. Each layer plays a role in maintaining the star's delicate balance. Yet even as the star continues its quiet work, another slow transformation is beginning. Helium in the core is gradually being consumed, just as hydrogen once was. The supply is not infinite. Over time, the carbon-oxygen core grows larger, slowly replacing the helium that once fueled this stage of the star's life. Gravity waits patiently. When the helium fuel begins to fade, the balance within the star will shift once again. The layered structure will become unstable, and new changes will begin to unfold. For now, though, the star continues its quiet creation. Carbon forms. Oxygen forms. The elements drift through the star's interior like seeds waiting to be carried outward into the galaxy. You watch the red giant glow softly in the dark, its immense atmosphere shining like a vast lantern across space. And within its hidden heart, the universe continues forging the atoms that will one day build entire worlds. But even this remarkable stage cannot last forever. Because as the star creates heavier and heavier elements, it slowly approaches a moment when gravity will once again demand its answer. You remain beside the great red giant as it continues its slow work in the darkness. For a long time, the star has lived as a quiet workshop of the universe. Deep inside its core, helium fusion has been creating heavier elements, carbon and oxygen, while shells of hydrogen and helium burn in layers around it. From afar, the star still appears calm. Its enormous atmosphere glows gently, spreading a warm reddish light into space. Vast currents of plasma rise and fall across its surface, moving slowly through the expanded outer layers. Yet deep within the star, the balance that has guided its life for so long is beginning to shift once again. The fuel that once powered the core is slowly fading. Helium, which ignited after the star became a red giant, has been steadily consumed by fusion. Over hundreds of thousands and millions of years, the helium atoms in the center have been transformed into carbon and oxygen. These heavier elements accumulate quietly in the core. And unlike hydrogen or helium, carbon and oxygen do not easily fuse under the current conditions inside the star. So the core begins to change. Without active fusion in the center to generate outward pressure, gravity once again tightens its grip. The enormous weight of the star presses inward on the carbon-oxygen core, compressing it further. The core begins to contract. As it shrinks, its temperature rises once again. Pressure grows. The atoms within the core are squeezed closer and closer together. Meanwhile, the shells of hydrogen and helium surrounding the core continue their nuclear reactions. These outer fusion layers generate large amounts of energy, pushing the star's outer atmosphere even farther outward. The red giant grows more unstable. Its outer layers pulse gently, expanding and contracting in slow rhythms that may take months or years to complete. Enormous waves move through the star's extended atmosphere, causing it to brighten and dim over time. You drift through the vast outer layers and feel the slow breathing of this aging star. The changes are subtle but relentless. Deep inside, gravity continues pressing inward. Temperature rises steadily. The carbon-oxygen core grows denser and denser. For stars that are small or moderate in mass, the core will eventually become so dense that it stops collapsing through an unusual effect of quantum physics called electron degeneracy pressure. This strange form of pressure arises when electrons are squeezed so tightly that they resist being forced closer together. But for more massive stars, the story becomes even more dramatic. If the star contains enough mass, the core can grow hot enough for carbon itself to ignite in nuclear fusion. Carbon fusion requires temperatures approaching 600 million degrees. Such extremes push the laws of physics to their limits. In these massive stars, new layers of fusion begin forming in the interior. Carbon fuses into heavier elements like neon and magnesium. Later, neon and oxygen may fuse as well, producing silicon and sulfur. Each stage burns faster than the last. Hydrogen fusion can last billions of years. Helium fusion may last millions. Carbon fusion may continue for only 1,000 years. Silicon fusion may last mere days. The star becomes a layered furnace. At the center lies the densest core. Around it are shells of burning elements, stacked one outside another like the layers of an onion. Hydrogen burns in the outer shell. Beneath it lies helium fusion. Deeper still are layers of carbon, oxygen, neon, and silicon fusion. Each layer releases enormous energy as it transforms lighter elements into heavier ones. But this process cannot continue forever, because there is one element that cannot release energy through fusion:
iron.
When a star's core begins producing iron, something fundamental changes. Fusing iron atoms does not release energy, it consumes energy instead. The star's nuclear engine begins to fail. Fusion has always been the force pushing outward against gravity. It has supported the star's weight for millions or billions of years. But once the core fills with iron, that support disappears. Gravity remains. Fusion fades. The delicate balance that has defined the star's life begins to collapse. You watch the enormous star glowing softly in space, its outer layers still drifting peacefully outward. To any distant observer, it might still appear majestic and calm. Yet inside, the star is approaching its final struggle. The core grows heavier with iron. Gravity presses inward more strongly with every passing moment. The layers of fusion surrounding the core burn faster and faster, trying desperately to maintain the balance. But the energy they produce is no longer enough. Eventually, the core reaches a critical point. The iron core becomes so massive that even electron degeneracy pressure can no longer support it. And when that moment arrives, the collapse begins. Not slowly, like the gentle transformations you have watched until now, but suddenly, violently. The core falls inward under its own gravity at tremendous speed. In less than a second, the central region of the star collapses inward, compressing matter to densities so extreme that atoms themselves are crushed together. But that moment has not quite arrived yet. For now, the star still holds itself together, its layered furnace burning with incredible intensity as gravity prepares its final move. You drift beside the aging giant and sense the quiet tension building deep within its heart. The star has spent millions of years forging the elements of the universe. Now gravity is preparing to reshape those elements once more. And soon, the star will release them in a way that will illuminate the entire galaxy. You hover near the red giant, watching the calm glow of its enormous outer layers. For eons, it has shone steadily, slowly transforming elements deep within its core. Carbon and oxygen, neon and silicon, each created with patient care over millions of years, now lie concentrated in the heart of the star. But this tranquility is deceiving. Gravity presses relentlessly inward, the iron-rich core no longer able to support itself. The balance that has maintained the star for so long is gone. Even the fusion in the surrounding layers, burning furiously in a desperate attempt to resist collapse, cannot overcome the overwhelming force of gravity. Then, in an instant measured by the cosmos as a fraction of a heartbeat, everything changes. The core collapses. Matter falls inward with unimaginable speed. The densest layers are compressed into a sphere smaller than the Earth, yet containing more mass than the Sun. Atomic nuclei are squeezed together until electrons merge with protons, creating neutrons in a burst of energy. The very fabric of matter is altered in this extreme environment. The outer layers of the star, once drifting peacefully across space, now find themselves unsupported. Within seconds, they plummet toward the collapsing core, accelerating to a significant fraction of the speed of light. The pressure and density in the core skyrocket until the collapse can no longer be contained. And then it happens. The core rebounds. The imploding matter slams against the incompressible neutron-rich center, creating a shockwave that races outward through the star. The energy released is staggering, comparable to the total energy the Sun will emit over its entire 10 billion-year life, discharged in mere moments. Inside the ejected shell, the elements mingle and combine. Carbon and oxygen enrich the interstellar medium, seeding clouds of gas and dust with the ingredients necessary for planets, moons, and eventually life. Every atom forged in the star's core now begins a new journey, traveling across space to join future generations of stars and worlds. The explosion may be catastrophic for the star itself, but it is generative for the universe. Creation often comes with destruction, and the supernova is a vivid reminder of the cyclical nature of cosmic life. The violent end of one star becomes the quiet beginning of many others. Some remnants of the core remain behind. If the star was massive enough, a neutron star forms, a sphere so dense that a single teaspoon of its matter would weigh billions of tons. In the most extreme cases, the core collapses even further, forming a black hole, a region where gravity is so intense that not even light can escape. These remnants silently continue to shape the universe, their presence felt across vast distances. Meanwhile, the shockwave continues to expand into space, stirring nearby clouds of gas and dust. Over time, this movement triggers new collapses in other regions of the galaxy, sparking the formation of fresh nebulae. And within these clouds, new stars will eventually ignite, continuing the endless cycle of stellar birth, life, and death. As you drift among the remnants of the exploded star, you notice the delicate beauty in the chaos. The material once confined within the core is now free to roam the cosmos. The elements that formed over millions of years in the heart of the star are now scattered across the galaxy, quietly awaiting their next purpose. The supernova is both an ending and a beginning. The star that once shone steadily, nurturing its own balance, has released its life force into the universe. Its energy, once contained, now travels outward, influencing everything it touches. Planets, asteroids, future stars, and even life itself will owe their existence to this magnificent event. Even in the destruction, the star continues to give. Its matter enriches the universe. Its energy reshapes the surroundings. Its light reaches across space and time, a reminder of the enduring cycles of creation. You take a moment to absorb the scale of the transformation. What seemed like a violent catastrophe is also a moment of profound creation. Every atom now moving through space carries a story, the story of a star that lived, grew, and ultimately gave itself back to the cosmos. Some of the heavier elements formed in the star, like gold, silver, and uranium, will never fuse again in ordinary stars. They exist only because of this violent release, scattered across the galaxy by the supernova's immense energy. In this way, even death in the cosmos carries with it the seeds of life, beauty, and complexity. And yet, the star's journey is not entirely over. In the heart of the remnant, a dense neutron star may spin rapidly, emitting beams of radiation that sweep across space like lighthouse signals. Or if a black hole has formed, it quietly bends space-time around it, influencing nearby matter and energy in ways that can shape entire star systems. The supernova fades gradually. Its initial brightness diminishes, the outward rush of material slows, and the once expanding cloud of gas begins to cool. But the echoes of the explosion remain, etched across light years of space. You sense the quiet aftermath, the lingering energy, the enriched material, and the subtle influence on the galaxy that surrounds it. And as the last vestiges of light and matter drift through the darkness, you realize that endings in the universe are never final. Each star's death feeds the next generation. Each supernova enriches the galaxy, laying the foundations for new worlds. Even in the quiet aftermath, creation continues. You leave the glowing remnants behind and drift toward the surrounding nebulae, where new clouds of gas and dust have begun forming. Somewhere in those clouds, future stars will ignite. The elements forged in this star, the carbon, oxygen, and heavier atoms, will one day find their way into these newborn suns, into planets, and perhaps even into living beings who will gaze up at the night sky, unaware of the journey that brought them there. In this quiet reflection, you understand the profound truth of the cosmos. Death is not a conclusion, but a transformation. The supernova's brilliance is brief, yet its influence echoes across space and time, a subtle reminder that creation often arises from endings. And as the shockwave drifts further into the cosmos, carrying the ingredients of future worlds, you realize that this star, though gone in its original form, has already begun to shape the universe in ways both gentle and eternal, leading you to wonder what new cycles of life await in the clouds of stardust ahead. The brilliance of the supernova gradually fades. The intense flash of light that once outshone galaxies diminishes into the vast darkness of space. Outward-moving gases slow, cool, and drift silently through the cosmic void. Yet even as the fire of the explosion recedes, something remarkable remains at the heart of the star. The remnant, dense and enigmatic, a memory of the immense energy that once blazed outward. You drift closer, curious to witness this final stage of stellar evolution. Depending on the star's original mass, what remains can take different forms. For stars not massive enough to collapse fully into a black hole, a neutron star emerges. This is a compact sphere composed almost entirely of neutrons, particles formed when the collapsing core's protons and electrons merge under the crushing pressure of gravity. A single teaspoon of neutron star material would weigh billions of tons on Earth. Its density is almost unimaginable. The matter inside is packed so tightly that atoms themselves cease to exist in the way you know them. Despite its tiny size, often only about 20 kilometers across, the neutron star contains more mass than the Sun once did. Gravity is extreme, yet contained within this small sphere. Many neutron stars spin rapidly, rotating multiple times per second, their magnetic fields billions of times stronger than anything experienced on Earth. Some emit beams of radiation that sweep across space like cosmic lighthouses. These pulsars, so-called because of the pulsing light they send, are the enduring echoes of the star's former brilliance. For the most massive stars, the remnant goes even further. Gravity overwhelms all resistance, and the core collapses beyond the limits of neutron degeneracy pressure, forming a black hole. Here, space-time itself curves so intensely that not even light can escape. To an outside observer, the star's visible life has ended completely. Yet in the surrounding region, the black hole influences matter and energy profoundly, bending light, drawing in gas and dust, and warping the space around it. It is an invisible presence, quiet yet extraordinarily powerful. Even though the supernova has ejected the star's outer layers, enriching the cosmos with carbon, oxygen, and heavier elements, these remnants continue to shape their environment. The neutron star or black hole may interact with surrounding gas clouds, companion stars, or interstellar material. Their gravitational pull can trigger new star formation, guiding clouds of dust and gas into new collapses. In this way, the star's legacy continues, unseen but tangible. You float nearby, observing the stillness after the storm of the supernova. The nebula left behind is glowing softly, a veil of gas and dust stretched across light years. Within this debris lie the seeds of new stars, planets, and eventually life. The star's elements, the ones forged over millions of years of quiet fusion and violent supernova, have begun their journey into the universe once more. The remnant itself is a reminder of the extremes of physics. In the neutron star, matter is compressed into an almost inconceivable density. Electrons and protons no longer exist separately. The core is a sea of neutrons. In a black hole, matter is crushed into a singularity where gravity is infinite and space-time itself reaches the limits of understanding. Both remnants are testaments to the immense forces that govern the cosmos. Even as the remnants seem motionless, they are far from inert. Neutron stars may spin with incredible speed, generating electromagnetic radiation, while black holes can pull in nearby matter, forming accretion disks that glow brightly in X-rays. Surrounding material may spiral inward, heated to extraordinary temperatures before disappearing beyond the event horizon. These remnants continue to shape space around them, a subtle yet profound influence on the next generation of stars and planets. You consider the paradox of these remnants. On one hand, they are silent, hidden, and in many ways invisible to the naked eye. On the other, their existence dictates the behavior of matter and energy in their surroundings. A neutron star or black hole might quietly orchestrate the formation of new stars, determining where gas clouds collapse or where disks of material swirl to form new planetary systems. Even death, in this cosmic sense, is generative. The star's visible life has ended, Yet its matter, its energy, and its gravitational influence continue to play a role in shaping the universe. Its light is gone, but its presence endures, subtle and profound. Some of the elements expelled in the supernova will form new stars, while others will gather into planets, asteroids, or comets. The carbon and oxygen produced in the star's core may one day form the basis for oceans and atmospheres, or perhaps even for life itself. Every atom in your own body, in some distant sense, may have been forged in a star like this, a quiet reminder of the enduring cycles of creation. As you drift further, you notice that the supernova's remnants slowly mix with surrounding interstellar clouds. These clouds, enriched by the star's elements, drift gently across the galaxy, sometimes colliding, sometimes collapsing under their own gravity. In these motions, new stars will eventually form. The neutron star or black hole at the center may remain, quietly influencing the gravitational landscape, ensuring that the cycle of stellar birth and death continues. The star's story is no longer about its surface light, its nuclear fusion, or its outward glow. It is about influence, about legacy, about the quiet yet profound ways in which matter and energy shape the cosmos. In the remnants, the universe retains the memory of the star's life, encoded in the elements it created, in the dense heart that survives, and in the waves of energy that ripple through space. You sense that even in death, the star is far from gone. It continues to participate in the grand processes of the cosmos, guiding the motions of matter, enriching interstellar clouds, and contributing to the conditions that will allow future stars, planets, and perhaps life itself to emerge. Its existence persists in subtle, enduring ways that defy the ordinary sense of life and death. And as you leave the quiet remnant behind, drifting through the enriched nebula and toward distant clouds of gas and dust, you feel the gentle continuity of cosmic cycles. Stars are born, live, die, and leave remnants that quietly shape the universe. Creation flows from destruction, and endings become beginnings in a rhythm that stretches across billions of years. Even after the light has faded, the star continues to guide the universe, a silent presence in the dark, dense, and mysterious reaches of space. And in this enduring presence, you sense the quiet, patient promise of what is yet to come. You float gently through the quiet aftermath of the supernova. The violent brilliance has long since faded, leaving only the soft glow of enriched gas and dust drifting across space. Carbon, oxygen, iron, and countless other elements now mix with hydrogen and helium in vast, invisible currents. They move slowly, carried along by gravity and the faint pressure of stellar winds. Though motion is gradual, the process is ceaseless. Creation continues quietly, far from the eyes of observers, in a rhythm older than time itself. These clouds of gas and dust, sometimes called nebulae, contain the seeds of new beginnings. Over millions of years, gravity gathers these particles into denser regions, drawing them closer together. Slowly, spiraling currents form, and within them, material begins to coalesce. You witness the subtle motions of the universe at work, clumps merging, colliding, and settling, each movement shaping the eventual form of new stars and planetary systems. The elements once forged in the heart of a massive star now take part in this grand process. Carbon may become part of a rocky planet. Oxygen may join a nascent atmosphere. Iron may sink deep into the core of a newly forming world. Every atom carries the memory of the star's long life, from the quiet fusion of hydrogen and helium to the explosive dispersal of a supernova. In this way, the universe recycles itself endlessly, weaving old matter into new forms. You drift through the clouds, noticing how even the tiniest particles play a role. Dust grains clump together, forming microscopic structures that will eventually seed planets. Gas molecules swirl in slow spirals, forming the wombs of new stars. Gravity works patiently, like a quiet sculptor, guiding the shapes of what will emerge. The process is neither hurried nor chaotic. It is deliberate, inevitable, and beautiful. In these clouds, stars will eventually ignite again. Hydrogen will fuse into helium, just as it did in the star that once exploded. Helium will build heavier elements, continuing the grand cycle of stellar life. Some of these future stars will become red giants, producing carbon, oxygen, and heavier elements. Others may live short, brilliant lives, collapsing into neutron stars or black holes. The universe repeats this dance, generation after generation, never stopping, never tiring. And within these new worlds, life may one day arise. The carbon and oxygen created in the heart of a long-dead star could join with other elements to form molecules essential for life. Water may gather on the surface of a planet, drawing from oxygen and hydrogen. Organic molecules may assemble, building ever more complex structures. The atoms that once belonged to a star may become part of oceans, mountains, or living beings. You begin to sense something extraordinary, a continuity that spans billions of years. The death of one star becomes the birth of many others. The supernova that seemed catastrophic transforms into a gentle force of creation. Matter is never lost. It is merely reshaped, reorganized, and reused in infinite combinations. Time flows, and with it, the universe evolves. As you drift through these cosmic clouds, you realize the personal connection to the stardust around you. The elements in your body, the carbon in your cells, the oxygen you breathe, the calcium in your bones, were all forged in stars that lived and died long before the Earth existed. You are part of this endless cycle, made from the very matter that once shone as brilliant stars. In a sense, you are both ancient and eternal, a continuation of the universe's grand, patient rhythm. The nebula around you begins to coalesce into denser pockets. Gravity draws the gas and dust inward, slowly forming protostars. These young stars are the next generation, waiting for their moment to ignite. The light that will emerge from them will travel across space for millennia, touching distant planets, perhaps even life forms yet to exist. You witness the universe preparing its next act, a subtle choreography that ensures the continuation of cosmic cycles. Time stretches around you, immense and incomprehensible. Millions of years pass in what feels like moments. You watch a protostar begin to glow faintly, a small spark of fusion igniting at its core. Around it, the dust and gas continue to orbit, eventually forming planets, moons, and other structures. The elements from previous stars, scattered across space, have now begun a new chapter, slowly building a new world. Some regions of the nebula remain diffuse and quiet, while others collapse more rapidly, forming clusters of stars. Each star carries the potential to repeat the processes you have witnessed: hydrogen burning into helium, helium into heavier elements, eventual swelling into red giants, and perhaps the final explosive release of a supernova. The cycle of birth, life, death, and renewal continues without pause, a cosmic rhythm that neither hurries nor halts. And as you drift farther through this star-forming region, you notice that the universe has no true ending. Stars die, but their elements are reborn in countless ways. Nebulae form, collapse, and ignite new suns. Planets coalesce and evolve, sometimes giving rise to life. Every atom carries the legacy of the past, even as it participates in the present and the future. The universe is an eternal cycle, endlessly weaving matter, energy, and life into new forms. In this meditative drift, you understand the profound connection between all things. The stardust scattered across space, the atoms that make up your body, and the planets forming in distant nebulae are all part of the same ongoing story. You feel a sense of belonging, a quiet awareness that you, too, are an integral part of this vast, patient cycle. The elements from ancient stars continue to journey across space, slowly joining with gas and dust, forming new stars and planets. The universe does not end. It transforms endlessly. Each star's death is a prelude to creation, each explosion a seed of renewal. And in this grand rhythm, you realize something remarkable. You are made of stardust. Every part of you once shone in the heart of a star, lived through cosmic cycles, and now participates in the endless dance of matter and energy. As you drift through the quiet cosmos, surrounded by glowing nebulae and the scattered remnants of ancient stars, you sense the vastness of time and space and the delicate continuity that links everything. The universe is not a collection of separate objects, but a continuous, ever-changing flow. Life, death, and creation are inseparable, and the cycles of stars and matter will continue long after you and I are gone. And as the cosmic clouds swirl gently around you, carrying the atoms that once belonged to stars long vanished, you realize the profound truth of the universe. Everything is connected, everything transforms, and even in the quiet darkness of space, creation never truly ends. The stardust drifts onward, patient, enduring, and eternal, waiting for the next spark of light to begin again.